So just to mention that we'll be recording today's session. So if you have any concerns, please mute yourself and participate in the discussion using the chat box function provided within Teams. So like any other session, can we have someone to volunteer to be our note taker for the session?
Yeah, I pre-volunteered. I think it's my turn after a year of shirking that responsibility to others. So I will diligently be the note taker this time.
Great, thank you. Iwana was our note taker the last time and she was brilliant. Thank you, Iwana. Yeah, so for those joining us for the first time, the MECS Field Seminar Series is a fortnightly event that seeks to build a community of MECS Field researchers and also to share experiences with designing and implementing different methodologies across the MECS program. So today, I don't think there are so many of us, so we could do the usual, which is a quick round of intros. I have already introduced myself. So I am Bridget. I'm a research associate on the program and also serve as link researcher for Ghana and Rwanda. So yeah, nice to meet you all. Now, who is next? I will do John Leary. John Leary, please go next.
So yeah, it's John Leary, senior researcher working at Loughborough University and GAMOS. I'm co-convener with Bridget at the MECS Field Methods. And Karen, of course.
Right, okay. Next will be Will Coley. Will?
Hi, Will Coley from Strathclyde. I work mostly as for Malawi, also on the global market assessment for electric cooking.
Perfect. Moving on, Nigel Scott.
Hi, I'm Nigel Scott. I'm a director at GAMOS here in Reading and supporting various parts of the MECS program. Thanks.
Perfect. Thank you very much. The next on my screen will be Meron.
Hi everyone, Meron Tesfa-Mikael from UCL, also a MECS researcher.
Perfect, thank you. Next on my screen, Richard Seif. Hi Richard, could you introduce yourself, please? I think Richard is having some issues. We'll move on to Biraj from PETA.
So hello everyone, I am Biraj Gautam. I work with People Energy and Environment Development Association, PETA, NGO based in Kathmandu. So hello to everyone from Kathmandu. Thank you.
Great, thank you. Welcome. Next on my screen will be Nigel Monk.
Hi everybody, Nigel Monk, Research Associate. I'll introduce myself more fully in my talk in a minute.
Thank you very much. Next, beautiful Iwana on the screen.
Here I am. Thanks, Bridget. My name is Ivana. I'm a research associate at Loughborough, and I work on the humanitarian energy stream.
Thank you, Iwana. Next on my screen is Nick Russo. Nick?
Hi, everyone. Nick Russo. I'm one of the so-called international liaison managers in the MECS program. My work is with companies that make cooking devices, trying to understand how we can help them to bring new devices into the markets we're working with.
Perfect. Now I have let's see, I have Katie. That has to be Karen. Karen, do you want to go next?
Yes, thank you. I am Karin Troncoso. I am research associate at Loughborough University and linked researcher for Nepal and Nigeria, and working with gender and leave no one behind and the health streams.
Perfect. Thank you, Karen. Next, I have Richard Blanchard. Richard, do you want to introduce yourself, please?
Yeah. Hi, everybody. I'm Richard Blanchard. I'm I suppose a Loughborough co-investigator for this program, and I'm sort of helping lead the technical work at CREST.
Perfect. Thank you, Richard. Next, I have William Clements.
Hi, everyone. I'm Will Clements. I'm a PhD student at Bristol University, and I'm looking at electric cooking for Nepal. So I work with Biraj.
Thank you very much, Will. I have Martin.
Afternoon, everyone. My name is Martin Price. I'm a researcher at GAMOS, I'm link researcher for Myanmar and Zambia, and I also work on urban-related issues for the program.
Thanks, Martin. I have Isahak. Have I mentioned your name properly?
Yes, I'm Isaac Esteve. I work for Rocky Mountain Institute as Africa specialist based in Addis Ababa and actually engaged with this MECS study for Nigeria.
Okay, thank you very much. Let's see. I have Eduardo Sanchez.
Yeah. Good afternoon. My name is Eduardo. I'm researching in a technical University of Madrid in planning, in integrated planning, cooking, and electricity. Thank you.
Perfect. Thanks, Eduardo. I have John Barton.
Good afternoon. My name is John Barton, CREST, Research Associate, working on technical matters with Richard Blanchard and Nigel.
Perfect. Thank you. Next I have Kelly Carlin.
Good morning from Minnesota in the U.S. My name is Kelly, and I'm with RMI along with Isaac Esteve, and working on the Nigeria Clean Cooking Knowledge Hub project.
Thank you, Kelly. Welcome. Next I have Matthew Little.
Hi there. I'm Matthew Little. I'm a research associate at CREST at Loughborough, part of Richard's team. Not actually working on the electric cooking. I'm working on solar home systems and productive uses of energy for deployment in Tanzania. But I in the same lab with Nigel and John, so know a bit about that.
Thanks. Welcome. I have Vimbai next. Vimbai, go ahead.
Hi everyone, I'm Vimbai and I'm an RA for Gamos, and I'm currently working on communications and the MECS Plus website.
Great, thanks Vimbai. I have Soma. I'm sorry if I didn't mention your name properly. Do you want to go next? Is this Somia? Okay, there's some silence, so I suppose not. Sorry, can you please introduce yourself if I have missed you out during the introductions, please? Chris Mullen. You can go next. Yeah, hi, Chris.
Hi. Yeah, sorry, I joined a little bit late. Yeah, I'm Chris Mullen from Newcastle University, working with the MECS modelers, looking at electrical demand on networks and mini grids and that kind of thing.
Okay, perfect. Have I left anyone out? If I have left you out, please introduce yourself in the next few seconds.
Yeah, hello, I'm Martin Bliss. I work at Loughborough University as a researcher, and working in a group with Richard on the technical bits and pieces.
Thank you, Martin. Sorry for missing you out.
No
Anyone
problem.
else?
There's two Martins.
Anyone else left out? Right. Okay. So going ahead, thank you all for the introductions. So just to introduce today's session. Today's session, as you have seen from the emails, will be on, what we have titled MECS Cooking Power Stations Pilot Intervention Part 1, which will be the context and design fruition. So this will be the first in a series of seminars that will take place over the coming year on the development and field trialing of a set of battery-supported cooking devices designed by Loughborough University's Center for Renewable Energy Systems Technology, abbreviated as CREST, or the short form CREST. So we have two presenters today. We have two Nigels on today's program. The first is Dr. Nigel Scott of Gamos, and he will give us an overview of the planned field trials and all the MECS partners involved. And this will be followed by the other Nigel, who is Dr. Nigel Monk from CREST, who will give us a detailed understanding of what is being developed and tested. So before the presentations, please put all your comments and questions into the chat box, and I will bring them up during the dedicated Q&A. And also we will be providing a link to the recording and a copy of our discussion today, so no need to worry and if you miss anything during this session. Okay, so without further ado, we'll turn over the time to our first presenter, who is Dr. Nigel Scott from GAMIS. Nigel, if you're
Thanks,
ready,
Bridget.
please proceed. Yes.
Thank you. Yeah. Sorry, John was complaining that I haven't actually put together any slides for this presentation. So I think to call it a presentation is a bit generous. I was just going to talk for a few minutes to kind of give a bit of background before Nigel gives a proper presentation. Sorry, having two Nigels organising or talking on the same session, I think is very bad planning, but there you go. So, yeah, forgive me, I think a lot of you already know most of the background, but let me just sort of try and paint a bit of a picture. So the MECS program, as I'm sure you all know, is sort of focusing on clean energy, and it includes a whole range of energies, including LPG, biofuels, renewables, and so on, where they can be applied for cooking. But MECS has got a particular focus on electric cooking, simply because the received wisdom for many decades has been that cooking with electricity just isn't viable. And so that's where we focused a lot of our effort. And that obviously is where this particular activity with the MECS pilot is adding value, is answering some of those questions. So when we're thinking of cooking with electricity, we're thinking of three market segments, essentially, very broadly. So you've got grid connected, people who've got access to a national grid, but they may not be using it for cooking. People who are connected to a mini grid, and there's opportunities for cooking there, and people who have access to electricity through autonomous household systems. That'd be like your solar home system. And you can break those down. But so, for example, yeah, we talked about the grid connected. You can have people who've got a strong grid or a weak grid. So if you've got a strong grid, the way to introduce electric cooking there is just to persuade people to go out and buy an electric cooking appliance. There's no reason they couldn't just go out, get one, plug it in. And as Nick Russo said in his introduction, he's doing a lot of work with the manufacturers to try and stimulate an understanding of the potential market in some of these developed countries where MECS program is working. So in terms of technology, that's all catered for. You can buy stuff off the shelf. But where you've got a weak grid, there's opportunities there. So weak grids can form a number of different scenarios where people may not be able to cook. So for example, what we mean by weak grid is where there's a lot of brownouts, a lot of blackouts. And what we found from some of the MTF data, the World Bank multi-tier framework data we've looked at, some of those data sets have got an interesting set of questions to who do you have a metered connection, and where do you pay for your supply, and who do you pay? And you can quite clearly see that there's sections of the urban populations who are getting their electricity supply from another supply. So for example, that would be from landlords or from neighbors or a neighboring family, and they're getting some kind of an informal supply, and they're not allowed to cook, or for a number of reasons they are not cooking with electricity. So even within an urban grid connecting context, you are having a sizable proportion of people who may not be able to cook, put a conventional appliance onto the MECS. So that's an interesting segment which we need to think about. And then when we look at mini grids, those up until this point, mini grids have typically been supplying very small, modest electrical loads, radio, TV, charging phones, a few LEDs, that kind of thing. So of course, if you put a cooking device on that, maybe a sort of 600 to even a kilowatt of infrared hob or an induction hob onto that, that's introducing an enormous load onto a mini grid, which may not be able to support that. But there may be opportunities for introducing cooking and for using battery supported devices to make that transition onto mini grids much easier. So there's a number of market segments where battery supported cooking devices may have merit. So for example, we know in the Ethiopia's national energy plan, as a target for 35% of households to be supplied with off-grid electricity by 2025. So in these countries, even where they're aspiring to 100% of electrification, a sizable chunk of that is going to be not on the national grid. And so that again confirms there is a sizable market available for, and a large part of populations for whom some kind of a battery supported device could be of value. And that's what we're looking at now. So CREST, I'm sure Nigel will tell you more about the details, but CREST have now developed two models. One is an urban model, so that's an AC power hub that delivers AC and you can plug a normal appliance in. And the other is a rural device, which is a DC system, which is supplied with DC appliances. But Nigel will tell us more about that. So that's a bit of the background to why we are trying to, why we're interested in these battery supported devices. And the other thing I just wanted to talk about was what we're trying to do with the pilot field testing. So we wanted to address a couple of questions, which is sort of like, how will this technology perform in a real life situation, giving it to real cooks in real households? And obviously, Nigel and his team have designed a system based on a series of assumptions. So putting it into a practical context gives them the opportunity of seeing how it actually performs, what changes, if any, need to be done, for example, to sizing of components. And then we also want to know, how will cooks respond to using this technology? So that's more about the consumer side of things and how they adopt it over the course of time. And we've summarized up the purpose as to examine the technical performance and user experience of battery augmented electric cooking equipment. Now, that actually covers a whole multitude of sins, and I just wanted to quickly sort of skip through a number of the different partners in the MECS program who have an interest in the data and the findings that we're going to get from this field implementation of these pilots. So as mentioned, CREST themselves are interested in technical performance. So they're keen to test just how does it work under, or how does it hold up under working conditions. I mentioned also the user side of things. So the Loughborough geography team are interested in how compatible the devices are with traditional cooking practices. So they're looking at how they can encourage households to move towards a clean energy stack, and different ways of making the battery augmented. So understanding more about how people use it and their preferences, that would enable them to start, give them some understanding to help make or to come up with recommendations for how to make the augmented electric cooking more desirable, more sustainable. And they're also very keen to look into a bit more detail of the gender implications of cooking with these systems. The systems will be run out. The field testing in countries will be done by 3 partners in Kenya, Uganda, and Tanzania. And each of those partners has a vested interest in the whole electric cooking agenda, and they'll be particularly interested in the commercial viability of e-cooking. So is it socially, technically, and financially viable in the countries that they are working in? We've got a number of partners in the MECS program who are involved in various parts of a modeling exercise, and all of those partners are very keen to get real data back from these applications. So the modelers are most concerned with electrical load profiles and the implications of adding these kind of cooking loads to networks, be that low voltage networks connected to a grid, to mini grids. And they're also keen to try and explore different solutions to problems that they can identify. And this is going to be of enormous value when we're engaging with policymakers, regulators, utilities, and so on, who may have some concerns about the effects of sticking a load of electric cooking loads onto networks. So within the modelling team, we've got Strathclyde University. I think we've got Will here representing Strathclyde, they're interested in a whole range of issues, such as, for example, batteries, how are they used, how does that during network outages, and how that affects load profiles, what's the quality of the power that these devices are experiencing, what constitutes faults, They're keen on understanding load diversification. So when you've got multiple devices in a community, how different households using them at different times of day, and how can they collate the load to forecast development of control systems, for example. Newcastle University are very keen to get some information back on non-domestic loads to validate the household modelling that they've done to date. And within GAMOS, we've got Matt Leach will be looking at real data to put into his household load models. And Jackie will be looking again for field data to inform the life cycle analysis modeling she's doing, things like lifetime of components and so on. Liverpool University are investigating health impacts. They're very keen to understand the impacts of fuel stacking on household air pollution and risk to health. So they're going to ask for monitoring for household air pollution data. Birmingham University are looking at battery characterization. So how do the batteries physically degrade in the use in these hazardous conditions, and what other battery types might be more suitable and more cost effective would be their research question that they're looking into. And the Loughborough School of Design are particularly keen on user participation, the Living Labs methodology, which is a means for co-creating technical solutions based on the user experience. That's really engaging with the people who've got day-to-day experience of these appliances. So there's a lot more to be said, but that's just to try and communicate the breadth of interest in this program within the MECS team. So Bridget, can I hand back to you?
Great, thank you. Great timing. Yeah, so I'm very conscious of time because I am sure people have a lot of questions or comments. I have already seen one by Will, but I will address that later. So quickly, I'll pass that over to Nigel Monk. Nigel, take it away.
Thanks, Bridget. If John can share his screen and bring up the slides, that would be great. I assume they're there because I can see them. Hi, my name's Nigel Monk, commonly known as the other Nigel. I'm a research associate working at Loughborough University in the Centre for Renewable Energy Systems Technology, also known as CREST, as Bridget said. I'm working on some parts of the science, technology, engineering, design, production and manufacturing of some of the aspects of the physical realisation, if you like, of the research vehicle required in order to conduct this social, technical and economic research into the challenges facing MECS. So trust me, I have the easy task. I'll also chip in where I think my experience and knowledge can help in other areas, such as logistics, for example. I've only worked in academia for under 2 years. My background is in engineering at Rolls-Royce Aerospace and IT service delivery at Electronic Data Systems. I worked in operational research on manufacturing and logistics improvement projects, IT infrastructure, project and program management, program office management, and ISO 9001 quality assurance. And I mention these for two reasons. First, so that my close colleagues on the program can understand where my perspective comes from in the various debates that we have, and second, so that for any manufacturers involved, they can know there is some experience within the program should they wish to get involved with that. But my PhD was very recent, so I sharply remember that research starts with a question, and it's always the same question: what are you trying to discover? Next slide, please, John. The MECS pilot is a key component in the MECS program for lessons learning and evidence gathering of how e-cook ideas might be received and the technology perform in different geographical and cultural contexts. And that's pretty much what Nigel has just told us. I believe this sentence should be attributed to Nigel as well. CREST is not solely concerned with MECS research. CREST has been a leading research centre for nearly 25 years and is involved with many aspects of renewable energy. The Renewable Energy for Development team is led by my line manager, Richard Blanchard. Excuse me, I just scrolled too far in my script. And those are my colleagues on that team listed there. This part of today's seminar is about starting to describe the physical research vehicle that supports and enables this pilot study, but it's not meant to be the end of that conversation, so please make contact with myself or Richard if there's anything you'd like to become involved with. I'm now going to try to stop calling these devices the physical research vehicle and call them the MECS cooking power stations. There are a number of names or labels for solar home systems, solar power stations, etc. But this name embeds the best description of the purpose I can think of, and I'm keen to hear what meaning or understanding it conjures for the listeners. I may also lapse into referring to them as hubs or power hubs, since they're at the centre of the cooking activity. I'm briefly describing the journey to fruition, without this becoming a history lesson, to explain how and why we've arrived at the particular solutions I'll present. But the main focus will be on the solutions, what situations they address, who they're aimed at, how they're intended to be beneficial, what testing we have planned, and so on. So I apologise if that diminishes it for anybody. The product realization process or design process can be viewed as beginning at some point on the technology readiness level scale with requirements gathering. In a commercial setting, that might include market research, for example. In one sense, the whole intervention we're discussing here is purely information gathering, albeit from many perspectives and for several purposes. I think eCook on this slide describes the state of thinking at the start of 2019. This was the outcome of a lot of work leading up to MECS by particularly John Leary and Gamos, and I'm sure others. This is the eCook graphic there should be attributed to John, he tells me. This was at the beginning of the realization that cooking with electricity wins the carbon and indoor air pollution arguments easily, but that the economic equation needs the absolute best application of technology possible. That doesn't mean necessarily the application of the most advanced technology, nor necessarily a highly technical product like, say, the smartphone of cooking, nor do we shy away from that. It means the application of the most appropriate technology. For example, minimizing the energy used via highly efficient cooking appliances is necessary to allow the economics to become viable. This began the focus on adapting electric pressure cookers to local cooking styles and practices. I think the MECS program also embeds and perhaps began the acceptance of the notion that we, in the developed countries, cannot sit and invent and impose solutions. So, requirements gathering and appropriate technology beg the question, for whom are we searching for a solution? It's well known there are billions of individuals for whom MECS would bring personal benefits, as well as benefiting the world as a whole. But each individual has an individual situation, and technology is not necessarily flexible in that sense. For example, flexibility might require additional equipment that would add to costs and may be superfluous for most users. This expanse of individual circumstances forces us as designers to adopt stereotypical user personas as a design focus. MECS has published a significant working document on the subject of user personas, which can be found on their website. The paper presents a more sophisticated view of and framework for user personas that includes users' ability to pay and inclination to adopt new solutions or amend cultural traditions. But by mid-2019, our broad delineation of users was simply into these two groups: rural, largely off-grid cooks and urban or peri-urban cooks who have access to electricity but who still use significant amounts of charcoal for whatever reason. Following the requirements gathering, the next stage might be conceptual design. At this stage, alternative approaches are considered with an open mind, and then constraints are applied. This diagram was intended to show how choices in one area influenced what was feasible in others. It basically breaks down into an energy source, an energy store, and an energy use. I don't have time to describe it. One point I'd like to bring out is that the user's perspective begins right at the bottom right-hand corner of the slide, which is, sorry, I just got a pop-up, which is traditionally the end of a Westerner's story. So we carried this framework through to consider practical combinations to create overall solutions. But the crux of the design needed was to decide what voltage and type of current, direct current or alternator current, the system should operate at. There are a lot of constraints in that. This diagram was a mind map or influence diagram or a cognitive map that I drew nearly a year ago, I guess, from the information that's floating around then. It gives the state of technology available mid-2019. The one slide updates. That's the one, thank you. The diagram could be updated to a 2020 viewpoint, but I've left it to show the then situation. And again, I can't describe it fully. You can perhaps study it when the slides are circulated later. This was the time of transition between lead-based batteries, the search for new chemistries, the rise of lithium chemistries. Lithium technology had been advancing for several years in mobile devices, power tools, cars, but the direct replacement for the ubiquitous 12-volt lead-acid battery was only recently being adopted by renewable energy researchers and becoming available from renewable energy suppliers in the UK. And that was it. That was all you could get. 12 volts, 100 amp hours, rated as providing 1.2 kilowatt hours of energy. But the batteries would most definitely not deliver 1 kilowatt for 1 hour. Evidence for that, this data was collected by John Leary during his fieldwork in Tanzania. It shows the clear relationship between the discharge rate and the amount of energy that can be drawn from the same battery. And I'll come back to this battery performance characteristic later in the talk. We considered combining batteries to raise the voltage and reduce the current, but the key unknown was the design of the internal battery management system that's incorporated inside the battery. Very little information existed in the literature. The BMS is crucial to prevent overcharging individual cells, which can lead to thermal runaway and destruction of the battery and surroundings. But jumping ahead, there was an almost sudden and significant shift in battery technology. 24-volt lithium iron phosphate batteries, which incorporated an internal BMS that integrated with external systems, became available. One example is the Victron Energy Blue Power System, which this diagram shows from one of their user manuals. That's basically, if you look at the top left, there are 6 batteries in 3 parallel 2 series configuration. Each battery will have an internal battery management system to do the cell balancing, but the grey wires link via a serial bus to the external battery management system that keeps them all aligned. There's no way that a small research group like CREST could design that. It would take skilled electronic engineers, a dozen of them, at least a year to do that. And these suddenly became available. Now, as it happens, one of those, we've got a couple of these batteries. BMS picture, John. One of them happened to have a loose lid, so we got to look inside at what the BMS looks like. This is a 12.8 volt lithium battery. It's a 4S2P. They're prismatic cells, so they're sort of square. The balanced circuitry is replicated 3 times with a communications module at the end that leads to the serial bus. And I don't understand how it works any more than that. But this new battery technology allowed a simplified approach to the system design, because it was now viable to either invert the battery up to AC mains voltage or provide medium DC power while still limiting the discharge rates to around 0.5 C. I'll come back to the discharge rate question at the end. At the same time as studying EPC behavior through 2019, we imported 2 solar power hubs directly from a Chinese manufacturer, Sun's Energy. These were systems typical of 2019 products. We stripped them down, analysed them, created schematics, but they are relatively low power output and include some functionality which is undesirable for the MECS situation, where we're trying to constrain the use of our solutions to cooking and not general domestic appliances such as TVs, fans, etc. Those are low power loads which are already served by the solar home system industry, and besides, that generally involve burning charcoal. Nonetheless, the 2 hubs introduced us to Sun's Energy, who were eager to work with MECS, and Richard visited the factory in early 2020 in China and was very nearly still there now, stranded by the pandemic travel restrictions, but we're pleased to have him back, really. We worked with the manufacturer to design a system which went beyond their normal range. I like to use the analogy of a baker that normally, that's all right, John, I've added this bit, that normally produces small buns or rolls. We ask them to make a big loaf. The approach of using an established solar home system manufacturer allows the advantage of foreshortening the design iteration process. Indeed, the development was free of charge, but doing so carries some risk, and we're working through the detailed design of the 2 cooking power stations right now because after something of a hiatus caused by the pandemic, samples of the 2 systems arrived at Loughborough just over 2 weeks ago. A major advantage of working with an established solar home system manufacturer is that the systems are immediately commercially available. You just need money and a large organisation to manage it. So, next slide please, John. The specification of the AC system is it's intended to buy an EPC in country to use with it, so that the particular product is familiar to that country. The battery included is an 8S4P, so it's 25.6 volts. Technically it's got 26 650 cylindrical cells in. There are 76 amp hour lithium iron phosphate cells. The battery capacity is 1.9 kilowatt hour, which is deliberately oversized to avoid being undersized. Undersized might lead to failed cooking events and negative outcomes, whereas oversized simply adds cost that can be easily recalculated for smaller batteries in future when we have experience of the size that is actually necessary. The internal BMS on this is designed to deliver 100 amps. And lithium iron phosphate was chosen because it's fundamentally safe. If you want to know, there's no native lithium at the cathode in the charged state, so that if the cell container ruptures, it won't react with the atmospheric moisture in the way that lithium ion or lithium polymer chemistries will. The value proposition around the AC hubs is that for urban or peri-urban users with access to a weak grid who regularly experience power outages, that instead of lighting the charcoal burners when the mains fails and probably continuing using the charcoal burner once it's lit, the battery will allow electric cooking to continue, saving the purchase cost of charcoal and preventing the indoor air pollution. It may also benefit users where the tariffs are structured to deter high power devices, as Nigel was saying, most at low tariff rates and used to power the EPC without penalty. Naturally, there's some loss associated with charge discharge or round trip efficiency, which has to be offset from any benefit. And one might hope that in the future such a solution scaled up might be able to displace the very many diesel generators that more affluent urbanites choose to operate in the evenings. And these users may have sufficient grounds to mount a solar array, further assisting the value proposition. Next slide, John. This is the DC system. It uses the same battery, but with a 30 amp BMS. This is apparently common practice to use the same cells in different, what we would recognize as different batteries. This system is supplied with a 240 watt rice cooker and a 450 watt hot plate. Now, those power ratings are nominal, based on 25.6 volts. The power will vary as the battery discharges because this is a simple resistive heating element, and the Kirchhoff law, which I've just forgotten, applies. The voltage is set by the source and the current is drawn by the load. The only constant is the resistance in the load in this situation. At least we hope that the resistance in the cooking appliances is constant against current and temperature. In the past they haven't been. So these are relatively low power appliances that we've supplied. I forgot to mention we also supply LED lights. There are some USB ports for charging mobile phones and so forth to enhance the desirability or usability. So the relatively low power appliances, although the hot plate will be capable of frying for at least part of the battery discharge power, the problem is there are no safe DC EPCs available of any power rating that we're aware of. Keen to find out if anybody knows of them. Hold that thought from them. In the meantime, the hot plate could be used with a conventional pressure cooker. Tests were attempted on that setup during the summer, but the results were not acceptable, basically because the temperature in my garage at home went up and down with the weather. So the financial proposition is more problematic in the rural setting, because do users pay for the fuel? Is firewood free to collect? Or is the charcoal supply controlled and commercialised, or even militarised? I don't know. But I can imagine that maybe the emergency humanitarian support might be another opportunity for using off-grid systems, or there may be other ideas. An alternative for raising the appliance power might be to invert the DC battery back up to mains AC voltage and use commercial AC appliances, EPCs I mean. This is an alternative that can be tried at some point, depending on the degradation of the battery in the AC unit after providing such power requirements. However, having broken the catch-22 conundrum by supplying an adequately powerful DC power station, it is our intention to produce a research quantity of 600-watt DC EPCs and then work with in-country manufacturers to create a supply chain for mass production. This will be my major task for next year. Whilst I may be the conductor, I won't be the whole orchestra, and even if I have to sit in for the design and production sections, there will need to be involvement from all MECS disciplines. So please watch out for an invitation to contribute to the requirements gathering phase. CREST have conducted tests on AC EPCs at lower power levels to determine the effect on efficiency, and these working papers are available on the MECS website. Finally, because there are so many technical performance unknowns, particularly around the battery performance degradation, we're now beginning battery characterization tests. This information is simply not available from lithium battery manufacturers. I suspect the cooking application combines a unique set of demands on the battery. Colleague Martin Bliss has built a test rig to do this, which entails some novel approaches, and we're also engaged with Birmingham University to do the cell testing. The other type of testing, which I plan to do in the very near future, is to address the key question that users might have. Excuse me 1 second. Which might be, what and how much can I cook? So I'll be conducting some basic cooking capability trials, and these data will be included in the cooking power station user manuals. This was a suggestion from John Leary, which, like all good ideas, requires considerable effort to obtain good data, but it will be worthwhile. In summary, the design process has come full circle, and we've reached the selling stage. MECS now need to search for participants whose circumstances match those in which we imagine these solutions will be most beneficial. We hope that's a significant proportion of the several billion individuals, and we'll receive feedback and consider the next evolution or maybe evolutionary branch of this type of solution. I would say that introducing advanced technology may not be the path to resolution in and of itself, but without viable technical products, the transition to MECS can't happen. And because the economic argument is dependent on future technological developments, in batteries for example, the technology introduced will, by definition, be advanced. The organisational effort required for this scale of intervention is considerable, and the logistics is something that will be explored in other field method seminars. But to finish, what are we trying to discover? CREST is trying to discover the limits of technology to support MECS, and those facts will move the debate forwards in the hands of skilled influencers, and that, by far, is the harder part of the task. Thank you.
Okay, thanks so much, Nigel. So, yeah, this was very informative and very much reminded me of my physics lessons back in school. So those of you who missed your lessons today, we are confronted with a lot of these very interesting phrases that I remember back in the day. But this shows some of the technological innovation feeding into the whole objective of changing the narrative. So I don't have a techie question, but I have one for you later on. But I'll go first to the questions in the chat. So earlier on, Will provided a link and was saying that if anyone is interested in what the projections are for grid versus off-grid and grid, mini-grid, and standalone energy access across different countries, he has a link that provides that sort of information. So earlier on during the presentation, Nigel Monk mentioned something about the MECS personas and how this is tailored to suit different user groups. So I have provided the link to that that document she showed in the presentation. So Chris has a techie question. So Chris is saying, you said energy capacity of AC system was 1.9 kilowatt hour. I didn't catch it. Was it for the DC system? I think that's for Nigel Monk.
Both batteries are the same capacity, so the cells are the same cells with the same amount of chemistry inside them. On top of that is a quite significant piece of electronics which contributes to the cost of the batteries quite a lot, and that determines how much current they will provide. If you think that the Chinese manufacturers try to minimize the production costs of their products, if a customer only wants a 30 amp capable battery, why would they put a 100 amp capable BMS in it? Because the cost of the components and just the cost of the bus bars between the cells varies a lot. And if they can save a tenth of a cent, when you multiply that by 3 billion, yeah, it becomes a significant amount of money. So the capacity of both batteries is the same. It's just the current draw that each will provide is different between the two systems.
Chris, does that answer your question?
Yeah, it does. Thanks, Nigel. Just to follow up, so would you get do you know if the electronics are more efficient on the DC system or not, or does it not make much difference because of the conversion?
Yes, of the overall system, the battery directly powers the, I take that back, that's a lie, it goes through a solar charge controller and then powers the appliances. The solar charge controller should be well over 95% efficient because it's just a switch basically, it just switches them in. The AC system, yes, it has to go through the inverter. In that case, it's a constant power output, so that hammers the battery because to draw 1 kilowatt as the battery voltage drops, the current has to go up, and it's the current which hurts the battery. So we can theorize what that'll be, but now we've got the systems, we need to do those battery characterization tests.
Yeah, interesting. Yeah, thanks.
Any other questions?
I can do a quick lab tour.
Yeah, I think I have one. I think that's a bit linked to the lab tour as well. So I wanted to ask, it's not a techie question, but what does the team do on a normal day? It's not, I have gotten what you normally do from your presentation, but just to present a less techie version of what you do on a normal day, and perhaps talk about some of the boxes behind you and what they mean.
Yeah, okay. Well, half the day is taken trying to keep up with everything that's going on the MECS program, to be honest, and that could take more than a full day if we allowed it. I'm sure everybody feels the same way. So yeah, it depends where we are. Largely the project management of bringing those cooking power stations into the country has had to be done by Richard because of the way that universities work. I'm just a fixed term contractor, so I don't have any authority to spend money, which is fair enough. I wouldn't trust me either with £40 million. But the upshot is that I can't have very meaningful conversations with potential suppliers, like the Chinese manufacturers. I can't commit the program to do anything. That has to go through Richard, and Richard has a full-time academic job, so that can slow things down. So that was that side. On the technical side of that, then we chipped in as and when. Otherwise, over the past year, it's been a lot of testing appliances, starting with electric pressure cookers, trying to understand how they work, taking them to pieces. I was desperate to show this.
Yeah.
This is the hot plate out of the bottom of an electric pressure cooker. It looks not much different from a normal hot plate. That's the reverse side of it. These two bits are where the electrical connection goes, and there's a resistive element runs around the outside, and then lots of spigots for mounting all sorts of stuff. So, and Jackie, for example, is very interested in this because she wants to know the manufacturing techniques, and I can tell her with 99% certainty that it's one of two. It's pressure die cast in an injection molding machine. The only thing I don't know is whether the front of it is put in first or whether it's all one injection. And I need to saw it up to find out. So this one behind this is some of the things that we've tested. Top row are 115 volts appliances, which we kind of ended up with rather too many. Can everybody still see that? I can only see Iwona, which is not a problem, but just wondering what everybody else can see.
Yeah.
So we ended up with a few too many of those, but that was just an idea of perhaps operating the system at 96 volts DC to reduce the power a little bit and to go multiply the batteries up. But we decided that 96 volts DC was not a safe DC voltage and dropped the idea. The next ones are the ones that are all instrumented. I can go a little closer. They're typical British EPCs that have got a whole load of thermocouples on them. Next shelf down is some other types of appliances, slow cookers, hot plates. These are called thermal cookers. They're basically vacuum insulated technological equivalents of a Wonder Bag. So you heat your meal up on a hot plate and then put it in there to carry on cooking, and it takes no more energy than the heat that's already in it. We've got some mini kettles that we're thinking of supplying later. We've got a whole load of batteries down the bottom. This is how a battery comes from, where is it? China, if it's not inside an appliance, because it has to be in a metal box. And that's one of our batteries. Right, jump up. So we're testing. The setup might look something like that. Let me zoom out a bit. It's hard to tell you. Oh, wait a minute. There's a whole bunch of power stations. You can't see them, can you? Because they're under the table. Yeah, well, that's boring. There's a power supply, a data logger, a pressure cooker, a hot plate, a big battery, and a whole load of wires. But what's more interesting is this doesn't actually belong to MECS. This is a big room that's heavily insulated, and if we're nice to the bloke that owns it, he might allow us to put the systems in there and test them at high temperatures, like they'll suffer in the countries they're going to. That's the whole lab behind me. Half of it's ours, half of it isn't. Crispin's in the corner, he's our PhD student. This is the test rig that Martin's put together. Lots of flashing lights, or not so many because he turned it off because it makes a lot of noise. That will be linked up to either a battery or a power station down there.
Yeah, Nigel. Great. Thanks for the virtual tour. Can anyone hear me?
Yes, I can hear you. I can't hear Nigel.
Yes.
Okay, great. Great, everyone is here. Okay, perfect. So the last question, not sure Nigel can answer at the moment. Nigel, Monk, can you hear me? Yeah, I think I'll mute him now if I can. Well, I can't. Hi, Nigel. Great. He's back. Okay, thanks, Nigel, for the tour. You have a question. Last question before we sign. We leave for today by Curly. He's asking, is there a range of costs for these hubs or stations?
Yes, but it's not a simple question. If you work on $1,000 for the system, that's the ex-factory price or the free on board cost. You then need to pay the shipping and the import duties, and then the for all the arrangements in country. And I can't give you a simple answer for that yet. We haven't worked it out, and it varies depending on what import tariffs various countries choose to impose. But it's less than $1,000. I can't remember offhand. It's not quite at the $500 mark, particularly when you include the duties and so forth. But you know, that's sort of for the future. This is proving the technology side.
Okay, perfect. So thanks everyone for taking part in this session. Especially a huge thank you to our presenters and the audience. So hopefully this session has given you some insights into all the things, all that innovation happening behind the scenes, ensuring that we can all change the narrative regarding clean cooking in all the different settings all around the world. So thank you all for coming, and see you all in 2 weeks when we explore another interesting research question or dimension or research happening on the MECS program. So thank you everyone for coming, and have a great day. Thank you so much. Bye-bye, everyone.
Thanks, Bridget. Thanks, Nigel. See you in a couple of weeks.
Thanks, everyone.
Thanks.
Yeah, thanks, Bridget. Well done. Bye.
Thank you. Bye.